One of the ways that we determine what's in a compound, especially for organic compounds, is by combustion. Organic compounds, especially, there's a wide variety of compounds out there. But if we burn it, well, we turn all the carbon into carbon dioxide, all the hydrogen goes into water. If there's oxygen present, that'll be part of the combustion process. And if there's nitrogen or other compounds, then it makes it a little bit more challenging. So the process, the steps, from the carbon dioxide, so we need to collect the carbon dioxide in water, get the mass of the carbon dioxide in water that is produced. So that's the goal with this. We have various adsorbers that can absorb just carbon dioxide. Different one will absorb just water. So we take the mass of the carbon dioxide, and from that we want to determine the moles of carbon and the mass of carbon. We're really after moles, but we need the mass to help us to figure out the amount of oxygen in the compound. So we get the moles and mass of carbon from carbon dioxide. From the mass of water, we want to determine the moles and mass of hydrogen also. So we've calculated mass of carbon, mass of hydrogen. We will have the mass of the original compound. So we subtract off the mass of carbon, mass of hydrogen from the mass of the original compound. And this will give us mass of oxygen. Now we convert that. That will be mass of oxygen in the compound. Not what we're using for combustion, but what's in the compound. Then we convert that mass of oxygen into moles. So now we have moles of carbon, moles of hydrogen, moles of oxygen. There'll be random moles. We divide by the smallest value to get to 1, and then numbers larger than 1. If there are any decimals, we look for the fraction, multiply all the moles by the denominator of the fraction to give us our subscripts for our empirical formula. So go through this. So we have a 0.500 grams of organic compound. We burn it, we get 0.687 grams of carbon dioxide and 0.562 grams of water. So for carbon, we take our carbon dioxide mass, convert it into moles. That would be moles of carbon dioxide. It's a 1-to-1 ratio to moles of carbon, so we get moles of carbon, 0.0156 moles of carbon. We multiply by the molar mass to get the atomic mass, to get the mass of carbon, 0.187 grams of carbon. Do the same thing for hydrogen from water. So we take our mass of water, don't seem to be showing the step of turning mass of water into moles, but I take the mass of water, 0.562. I divide by the molar mass of water, 18.02. That'll give me the 0.0312 moles of water. So I'm not showing the line of dividing 0.562 grams of water by 18.02 molar mass of water. So I get moles of water. In this case, we have 2 hydrogens in 1 water, so we multiply by the ratio of 2 hydrogens to 1 water. That gives moles of hydrogen, 0.0624 moles of hydrogen. Multiply by the atomic mass of hydrogen, and we end up getting the mass of hydrogen, 0.0629 grams of hydrogen. To figure out the oxygen compound, we take the original mass, 0.5 grams, we subtract off the mass of carbon, the mass of hydrogen, we're left with 0.25 grams of oxygen. We divide by its atomic mass, and we get the moles of oxygen, 0.0156 moles of oxygen. So now we have moles of carbon, moles of hydrogen, moles of oxygen, but the random numbers, so we divide all of them by the smallest value, and both carbon and oxygen had a similar small value of 0.0156. They both become 1. The hydrogen becomes 4, so that gives our empirical formula C1H4O1. We don't write the 1, so it becomes CH4O. So the molecular formula is really what we're after. So the molecular formula shows the ratio of the elements in the compound as we find it in nature. So for this one, we need to know the molar mass to be able to convert a empirical formula into a molecular formula. And we determine the molar mass of the empirical formula. Then we're going to do a ratio of the molar mass of the compound over the empirical mass. This should give us a whole number, this ratio. Then we multiply the empirical formula by that whole number, and that will become the molecular formula. So when we multiply the empirical formula, we're multiplying all the subscripts, including the ones that we don't write out. So this example, aspirin, we have the empirical formula, we have a molar mass. We figure out the empirical mass. Turns out the empirical mass and the molar mass are the same, so the ratio is 1, so the empirical formula is the molecular formula. So in this one, we are starting from a percent composition, and we have a molar mass, so that will allow us to go all the way to a molecular formula from the percent composition. So starting from the percent composition, we assume 100 grams, so our 38.7% carbon becomes 38.7 grams of carbon. We divide our mass of carbon by its atomic mass, we get 3.22 moles. So mass of hydrogen divided by its atomic mass gives us 9.64 moles. Mass of oxygen divided by its atomic mass gives us 3.22 moles. So we get our moles, we divide all three of them by the smallest value. This gives us 1 mole of carbon, 1 mole of oxygen, and 3 moles of hydrogen. So our empirical formula becomes CH3O. So we have our empirical formula, so to get the molecular formula, we first determine the empirical mass, add up the 1 carbon, 3 hydrogens, 1 oxygen. We get a empirical mass of 31.0 grams per mole. We do our molar mass 62 divided by the 31. We get a whole number multiplier of 2. We multiply all the subscripts in our CH3O by 2, and we end up with C2H6O2 as our molecular formula for this compound. So if we have our percent composition and our molar mass, we can do the same process to get the molecular formula. If we're not interested in getting the empirical formula, we have another way of going directly to the molecular formula from the percent composition and molar mass. In this case, what we do is that we assume that we have a molar mass amount of mass. So we're using our molar mass as our assumed amount of mass of the compound. So then what we do is we use our percent composition, turn it to decimal form, multiply the molar mass by the decimal form, and that will get the mass of each element. But this will be the mass of each element in the molecular formula of the compound. So we assume that we have molar mass, turn it into a mass of each element, and then we turn that into moles by dividing by the atomic mass of each element. And this point, we should have whole number values. There should be no decimals in this one. We should have whole number values. And these whole number values are the subscripts for the molecular formula, not the empirical formula. So to go through this, we have compound aluminum. Oxide aluminum has 52.9% aluminum, 40.7% oxygen, molar mass of 101.96 grams per mole. So we assume that we have 101.96 grams. So we multiply by a decimal version of 52.9, so we get 0.529 times 101.96, because it's 53.9 grams of aluminum. Do the same thing with oxygen. We get 48 grams of oxygen. We divide both those by their atomic masses, and we get 2 moles of aluminum and 3 moles of oxygen. So we get whole numbers right off the bat, and these are the subscripts of the molecular formula, Al2O3.